So in this video we're going to discuss DeMorgan's laws for logic. There are also DeMorgan's laws for set theory, which we'll talk about in a later video. So DeMorgan's laws for logic tell you how to negate statements with ands and ors in them. Okay, so let's let P and Q be logical statements. Then the following pairs of statements are logically equivalent. So first, the negation of P and Q, so not P and Q, is logically equivalent to not P or not Q. And not P or Q is logically equivalent to not P and not Q. It's really important to be able to properly negate statements. And this is one area where people sometimes run into trouble, is negating statements with the words and or in them. Later we'll also talk about negating statements with quantifiers in a later video, which is another area where people sometimes run into trouble. But for this video, we want to get used to using these laws called DeMorgan's laws. So how would we prove this theorem? Well, to prove it, we're just going to look at truth tables. So our first claim is that the negation of P and Q is logically equivalent to the statement not P or not Q. Okay, so we have to show that for all possible truth assignments of truth values to P and Q, the resulting truth values of the statement not P and Q and the statement not P or not Q always come out the same. Okay, and again, truth tables are the way to do that because simply they organize the information properly. It's the most efficient way to do it. So here's the truth table for the statement not P and Q. So if P and Q are both true, then P and Q is true. So the negation of P and Q is false. If P is true but Q is false, or if P is false but Q is true, then P and Q is false, if you recall from the truth table for and. But the negation of P and Q in that case is true. And then finally, if both P and Q are false, then of course P and Q is false, so the negation is true. Okay, so that's a truth table for the negation of P and Q, or not P and Q. And here's the truth table for not P or not Q. Okay, so if P and Q are both true, then not P and not Q are both false. So not P or not Q is false. If P is true and Q is false, then not P is false and not Q is true. So the disjunction not P or not Q is true. If P is false and Q is true, then not P is true and not Q is false. And so one of them is true, so not P or not Q is true. And then if both P and Q are false, then both not P and not Q are true. And so that would mean that the disjunction, the or statement, not P or not Q, is a true statement. Okay, so then now if you compare these truth tables, you can see that exactly the same inputs of truth values for P and Q give you exactly the same outputs of truth values for the statements not P and Q and the statement not P or not Q. So, as we can see then, for all possible truth assignments of truth values to P and Q, the resulting truth values of not P and Q and not P or not Q always come out the same. And therefore, we say that not P and Q is logically equivalent to not P or not Q. Okay, so that's always the way you would prove two logical statements are logically equivalent, is look at their truth values and show exactly this. Okay, what about the other claim that the negation of P or Q is logically equivalent to not P and not Q? Again, we have to show that for all possible truth assignments of truth values to P and Q, the resulting truth values of not P or Q and not P and not Q always come out to be the same. So again, the most efficient way to do this is with truth tables. So here's the truth table for the negation of P or Q. So we see the truth table for P or Q. If P is true and Q is true, P or Q is true. If P is true and Q is false, P or Q is true. If P is false and Q is true, then P or Q is true. And if both P and Q are false, then P or Q, it's the only case where P or Q is false. And then of course, if P or Q is true, then the negation of P or Q is false. And if P or Q is false, then the negation of P or Q is true. What about the truth table for the other statement? So let's look at the truth table now for not P and not Q. Okay, so you can see that if P is true, not P is false. If Q is true, not Q is false. Okay, so in the first line where we wind up with not P and not Q are both false, then not P and not Q is false. In the second line in the lower truth table, not P is false and not Q is true, so the conjunction of those two is false. The third line we have not P is true, but not Q is false, so the conjunction is false again. And then in the last line, we have not P and not Q are both true, and so the conjunction is true. So you can see then, again, the conclusion here is that for all possible truth assignments of truth values to P and Q, the resulting truth values of the negation of P or Q and not P and not Q always come out the same. And that exactly means, that's what we mean by logical equivalence. Not P or Q is logically equivalent to not P and not Q. Okay, so we've seen a proof now of DeMorgan's laws. Let's look at a couple of examples. Let's look at this statement. X is in A or X is not in B. So to negate this statement, we'll first observe that it is of the form P or Q, where P is the statement X is in A, and Q is the statement X is not in B. So the negation of this statement is logically equivalent to not P and not Q by DeMorgan's laws. Not P is going to be the statement X is not in A, and not Q is going to be the statement X is in B. Okay, so the negation of the statement X is in A or X is not in B, the negation of that is logically equivalent to X is not in A and X is not in B. Sorry, X is not in A and X is in B. Okay. So let's apply DeMorgan's laws to one more example. Consider the statement, the set C is closed and bounded. In this case, we have a statement of the form P and Q, where P is the statement the set C is closed, and Q is the statement the set C is bounded. So the negation not P and Q is logically equivalent to not P or not Q, according to DeMorgan's laws. So here not P is the statement the set C is not closed, and not Q is the statement the set C is not bounded. So the negation of the statement the set C is closed and bounded is logically equivalent to the set C is not closed or not bounded. Okay, and we'll see more sophisticated examples of this in class and in other videos, but for now that concludes this video. Thanks for listening.